Right. Good day, everyone. Today we want to look at conductivity of metals, alloys, and other materials. Just a recap on our last lecture, we looked at insulators and we defined what they are. We also defined our dielectrics, conductors, superconductors, semiconductors, and superconductors. And we also tried to delve in uh, on how these different electronic materials are applied. Today, we want to look at the conductivity of metals and alloys in terms of their effect of temperature, atomic level defects, impurities, and also what effect has some different kinds of processing, such as heat treatment, such as strengthening processes, how do they also affect conductivity of your metals and alloys. Then we're also going to look at the conduction in ionic materials, and lastly, a conduction in polymers. Okay. Now, as an introduction, the conductivity of a pure metal, and when we say a pure metal, we mean a metal that has no defects, which is a defect-free metal. It is generally determined by the electronic structure of the atoms. So this is what determines the conductivity of a pure defect-free metal. Its electronic structure of the atoms is the determining factor. But we can alter, or we can change, or we can have an effect on the conductivity of this pure metal. How do we do that? We can influence the mobility of the carriers, as we have said in our previous lectures. So we understood that from our previous lectures, we defined, um, we determined that mobility is proportional to the average drift velocity given by this equation that I've circled here. Okay, so we also defined as the drift velocity, the average drift velocity, as that velocity with which the charge carriers move in a determined direction as detected by the applied field. Okay, so that's how we defined average drift velocity. And also, um, now, the path of our charge carriers, and in this case, which is the electrons, is influenced by the internal fields due to the arrangement of the atoms in the solid, or also if there are imperfections that are also present in the lattice structure. Okay, now you can see here from this you can see here from this table, which shows a comparison of the electrical conductivity of several types of metals um, that we can use in the electronic industry. We can see that the electrical conductivity is reducing as we move from the top to down. And from the top, we have got our silver, copper, and gold. And out of bottom, we have got our stainless steel, which has got very low electrical conductivity. So we can see that most of the metals generally have got very good conductivity of of electricity. Some of them actually very high conductivity figures here, especially for those the ones that are on top. So at room temperature, at your RTP, metals generally have got high conductivity. Why? Because of the large numbers of free electrons that have been excited into what we called the empty states, which are above the Fermi level. We have discussed about this in our previous lecture. Right. So as also discussed in our previous lecture, we said it is very much convenient to discuss about the conduction in metals in terms of resistivity, which is the reciprocal of conductivity. Okay, so in this lecture, of course, we will alternate resistivity and conductivity, but for us to discuss efficiently conduction in metals, we will do that in terms of resistivity mostly. Okay. Now let's look at what is the mean free path. Right. What do we mean when we talk about the mean free path? When we talk about the mean free path, we are looking at the internal fields, um, that are influenced by the path of an electron. Okay. So when internal fields influence the path of an electron, the drift velocity, also the mobility of the charge carriers reduces. Okay, so when the field and the internal fields influence the path of an electron, okay, the drift velocity will reduce. Okay, so that is what we have determined that whenever there is a disturbance, or whenever remember, the arrangement of your atom is very important. The arrangement of your atom is very important. If they are arranged in a uniform and unique manner, then we are saying that the drift velocity might be okay. However, if you now begin to have some, maybe here you've got some impurities, then the path of your electrons begins to be disturbed, okay? And hence their mobility is actually disturbed. So this is the path of an electron. Maybe you've got an imperfection or an impurity into this alloy structure. So it begins to be disturbed into this atomic structure, sorry. Okay, so your mean free path is actually uh, defined as your lambda E, which is equals to your tau V. So what is the lambda E? So your lambda E, that's the mean free path, and then your tau is the average time that is taken between collisions, okay? And of course, we have already defined your V. So it means that um, a longer mean free path will actually permit higher mobilities and will actually permit higher conductivities, because we are saying that the our electron or our charge carrier will have a much longer distance to travel before it can collide into something, before it can collide into something here. Okay, so if this is a very large um, mean free path, then it means that your conduction is actually going to be very high. But if this mean free path is somewhere very small like this, maybe on up to here, so for starting from here, this point up to here, it means that your conductivity is actually going to be very low, because this charge carrier is only moving a very short distance and then it collides. Okay, so your conductivity is going to be reduced and your resistivity is actually going to be high in this case. Now, let's look at the effect of temperature first. Now, when the temperature of a metal increases, okay, then the thermal energy causes amplitudes of vibrations. There are certain vibrations that you begin to introduce when the temperature of a metal increases. And these vibrations actually increase as the temperature also increases. Okay, so what is the effect of this temperature increase? So this results in an increase in the scattering of the cross section of the atoms, or the defects that are actually in the lattice. Okay, so the atoms and the defects now act as larger targets for your interactions with electrons, and the interactions are now occur more frequently. The higher the vibration, the higher the amplitude, then the more frequent the interactions are. Okay, so ultimately, when the mean free path decreases, it means that the mobility of the electrons is actually affected and it's also reduced. And if the electrons or charge carriers do not are not mobile, it means that are not mobile fast enough. It means that your resistivity is increased. Okay, and your conduction is reduced. Okay, so here's an illustration on the two figures at the bottom here. They show you the movement of an electron through first A, which is your perfect structure, and your figure on your right, which is the a heated a crystal structure. So you can see that here on your on your left side here, you can see that the lattice structure is actually perfect. The distance between uh, the distance between um, the atoms is actually very uniform. Okay, so the distance is actually uniform as you go to the left and as you go in this direction, and as also as you go into this direction. Okay, so you can see that the distance is actually very much equal. So this is a perfect crystal. Okay, now let's look at your point B here, at your figure B. You can see that because of heating, there are now some energy gaps that are being created. There are now abnormal gaps that are being created here. Okay, and in here there is begins to be restriction. There begins to be restriction. There begins to be restriction. Some of the atoms maybe are in contact with the others. Okay, so this is not a uniform structure. As you can see, there are some spaces now between the atoms, and this actually this begins to disturb the flow of electrons. If you come here on your left side here, you can see that an electron can flow very uniformly on this path very well. Okay, but you can see here that this electron will struggle, it will collide, and because of this angle of collision, it might change direction and collide again with other atoms until it gets out of this lattice structure. Okay, so because of these differences and these spaces and these constrictions, this causes an increase in your resistivity and decrease in your mean free path, and also a decrease in your conductivity. Okay, now the change in resistivity of a pure metal when defined or as a function of a temperature, it can be estimated according to this formula here. So your rho is actually equals to rho pt, your brackets 1 plus your alpha rt delta t. Okay, so what is your rho? Your rho here represents the resistivity at any temperature, in this case. Okay, then your prt represents the resistivity at RTP, okay, that is usually at your 25 degrees. Then your delta T stands for the change in temperature, or basically the difference between the temperature of interest and your RT, okay. And then alpha is just a coefficient of your temperature resistivity, maybe for that kind of material that you are investigating, okay. Now, um, this dependence of thermal resistivity component on temperature. Now, what we're trying to define why thermal resistivity, okay, affects your why temperature affects your resistivity. So we say now this dependence of thermal resistivity component on temperature is due to the increase with temperature in thermal vibrations, as we said before, and also other lattice irregularities that begin to come up whenever you now change your lattice structure from a perfect to a one that is imperfect. Now you begin to introduce other irregularities such as your vacancies, as we saw in a previous slide, which now serve as electron scattering centers. Okay. Now let's look at this figure on your left here. You've got your temperature and you've got your electrical resistivity. Now it can be shown that resistivity and temperature have somewhat a linear relationship over a wide temperature range, as we can see here. So this is somewhat a linear temperature relationship, okay? So a linear positive relationship. As temperature increases, electrical resistivity also increases, okay? Which is the opposite of conductivity. When temperature increases, conductivity reduces. Okay, right. So on the right here, we show a table of resistivity coefficient for a few selected metals, from your beryllium to your platinum. You can see their resistivity at RTP here, and then you can see that the temperature coefficient lastly on the last column here. Okay, so uh, You can see the differences in the room temperature, resistivity of the different metals. You can compare them. Okay, for example, your beryllium is about 4. Then you've got your, where's your copper? It's about 1.6, which is generally low. Then you've got your gold about 2.3, okay, which is generally low. So this shows that these kind of metals, for example, your copper, which is low resistivity, which means that they've also got some high conductivity. Okay. Okay, this is a quiz for you just to practice. Okay, now let's look at the effect of atomic level defects on our resistivity, on our conductivity. Okay, so remember in our previous slide, we compared this one, which is a perfect crystal. This is a perfect crystal. And then we also compared to one which a crystal which is actually heated. Okay, right. So now in C, we are now introducing a crystal lattice. However, it now contains some defects. So this probably is a defect. Okay. So um, in the presence of this defect, okay, the scattering of electrons actually uh, results in them a reduction of mobility and conductivity. Okay, so the scattering of these electrons, okay, you can see this electron here, movement of electron, actually reduces the mobility and conductivity. Okay, so if this electron was supposed, you can see that the movement, it is colliding into these defects. It is colliding, maybe it's an impurity. So the presence of this impurity actually reduces the mean free path as well as the mobility and the conductivity of the charge carriers. Okay, now let's look at the effect of atomic level defects. Okay, so let's continue. Now, the imperfections in a crystal structures scatter electrons, okay, then also reduce the mobility and the conductivity of the metal, okay, so which means that they increase the resistivity, okay. So the increase in the resistivity due to the presence of a solid solution atoms is given by this formula here, okay. So your rho d, what is it? It is the increase in the resistivity due to the defects. And then you've got your B here, B, which is the coefficient of defect resistivity, then given by also now 1 minus your X is representing the atomic fraction of the impurity or solid solution atoms present. Okay, then of course you're close with your 1 minus X, then X here. Okay, so this is the formula for calculating the increase in resistivity due to defects. Okay, so what are some of the defects? So we can say that your vacancies, your dislocations, your grain boundaries are some of the defects that actually increase the resistivity of a metal. Okay, now each defect, okay, um, on its own contributes to the increase in the resistivity of the metal, such that we can say that the overall resistivity, which is your P total, is actually a total or the sum of different types of resistivity that are combined together. Okay, so we can have here your total resistivity being given by the resistivity, which is the contribution of thermal vibrations, which is your PT. You can have your resistivity due to the contribution of your impurities. Okay, then you can also have your resistivity, which is the contribution of the defect. Okay, so when these are added together, they give you the total resistivity. So this equation is actually popularly known as the Mathiassen's rule or Mathiassen's equation. Okay, so what do you mean? Therefore, the electrical resistivity of a metal can be concluded that it is due to a constant defect contribution, okay, PI and PD, and a variable temperature contribution. Okay, Right. Now, let's look at this figure here. This is your temperature on your x-axis and your electrical resistivity on your y-axis. Okay, so the figure is showing you a comparison of electrical resistivities, okay, of a perfect structure, of a perfect crystal structure, as well as the one material that is containing some defects. Okay, so we can see here that this, the first line here, is showing you how resistivity increases with temperature for a perfect crystal structure. Okay, so in this case, you can see this is the increase. Okay, now when we now have a defect, this line shifts upwards, and then it becomes this is now becomes the relationship of your resistivity and temperature when you now include a what, a defect. Okay, so this increase here is now the responsible component for this increase is now your defect. Without the defect, we expect the line to be like this. In the presence of a defect, it goes up and it becomes like this. Okay. Now, the concentration of these imperfections also depend on the temperature and composition, as well as the degree of the cold work that is being done on the specimen. Okay. Now, what are the effect of these impurities? Now, for the addition of a single impurity that forms a solid solution, the impurity resistivity, which is Pi, which is the impurity resistivity, is related now to the impurity concentration Ci, okay, being given by this formula here, okay? So that's the formula here, okay? So you've got your Pi um, being equal to your A, which is the composition independent constant. There's a product of your Ci, which is the impurity concentration, then 1 minus the impurity concentration. Now, this gives you what is called the impurity resistivity, or the contribution of your impurity to the resistivity. Okay, now remember, when you're talking of metals and you definitely try to alloy some, you create some alloys based on the properties and use of this material that you might want. Maybe you want it brass or something like that, where you mix two or more alloy phases. Now, this expression will now be given by this expression if you're now including an alloy. Okay. Right. This figure also shows the effect of impurities. In this case, we have got a copper nickel alloy, okay, a copper nickel alloy, showing you the influence of how nickel. So your x-axis is the composition of nickel, and this is your electrical resistivity, up to a percentage of about 50% nickel. So we can see that from zero here, when we've at zero, probably at zero here, we've got your 100%. This is 100% copper, 100% copper. Okay, the resistivity is quite low. But when you begin to introduce some nickel and nickel content up to 50%, we can see that the resistivity goes high. Okay, the resistivity begins to increase. So we say that the added nickel atoms in the copper matrix act as scattering centers and increases the concentration of nickel in the copper. And this increase in the concentration of copper results in an increase or in an enhancement in the resistivity. Okay, so that's clear for you. Okay. All right. So also here, we see now the effect of some processing and some strengthening activities that have been done on different types of metal. So we can see that different strengthening mechanisms and processing techniques actually affect the electrical properties of a metal in different ways. Okay, so for your pure copper, you can have your pure copper here having your your conductivity here of an alloy of an copper times 100. So in this case, it is actually 100. Okay, 100, maybe 100%. Okay, in this ratio times 100. Okay, then you say now your when your copper is deformed 80%, this is a reduction in this ratio. When you, for example, when you age copper with 2% beryllium, there's a drastic reduction in the ratio to around 23. And in this case, the least one is the solution treated copper with 2% beryllium, which gives us a ratio of around 18. So we can see a decrease in this ratio when we do some strengthening mechanisms of our metal. Okay. Now, different strengthening processes can include solid solution strengthening, alloying, and age hardening and dispersion. So your solid solution strengthening actually results in reduced mean free paths, and because of the random interstitial and substitutional atoms that begin to enter the perfect lattice structure, they begin to disturb the mean free path. Also, your alloying, for example, if you alloy your zinc, your copper, as the amount of the alloying element increases, the conductivity substantially decreases. Then your resistivity is also going up. Okay, when you do your edge hardening process, it means that the process results in longer mean free paths. Okay, longer mean free paths between precipitates as compared to the path between point defects. Hence, your conductivity is reduced to an extent that is less than the solid solution strengthening. Okay, now this figure illustrates the effect of solid solution strengthening and cold work on electrical conductivity of copper. Okay, so generally, this is your percentage deformation on your x-axis, and this is your conductivity on your y-axis. Okay, so we can see that conductivity of a pure copper is quite high here, and then your conductivity of your alloys here is quite low. Okay, when you do some deformations. So the strain hardening and grain size control have little effect actually on conductivity. Why? Because dislocations and grain boundaries are much further apart than in solid solution atoms. Hence, there are actually large volumes of metal that actually have got a long mean free path. Okay, so as a result, if any cold working processes is done, it is actually a very good way to increase the strength of a metallic conductor without hampering or affecting its electrical properties. Okay, and furthermore, even if you do your cold working, you can actually restore the strength by doing some low temperature heat treatment. Okay, now you can look at this graph, which shows again the relationship of electrical resistivity here on on your y-axis, as well as the temperature on your x-axis. This is for copper and some 3 copper, and here some 3 copper nickel alloys. We can clearly see here that as the nickel increases, here there is this one 0 nickel, 1.12 nickel, 2.16 nickel, 3.32 nickel. So we can clearly see that as the nickel increases, resistivity is also increasing. Okay, then we can also tell that from the x-axis, this is increase in temperature. As the temperature also increases, then there is also an increase in resistivity, hence the positive gradient of these lines here. Okay, if you take maybe for example at minus 100 degrees, we can see here that um, the Thermal impurity and deformation contributions to the resistivity. Here we can see this is your for your pure copper. This is copper at 1.12 here, and now this is the one that is deformed. Okay, so electric resistivity actually increases with deformation here. Okay, okay, so you've got your thermal ending here, resistivity for your thermal ending here. Then you've got your resistivity for your impurity, maybe ending somewhere here. Then resistivity when you now include also some deformation ending somewhere here. Okay, now let's look at conductivity of alloys. So alloys typically have got high resistivities. We explained the reason why. More than pure metals. Why? Because of the scattering of electrons due to the addition of these alloys. Okay, alloying elements. Okay, right. Now, compared to metals, the resistivity of alloys actually tends to be less stable in regards to temperature variation. Relatively high resistance alloys, such as your nickel chrome here, can actually be used in heating elements, such as your Kenthal wire in top head furnaces. So your Kenthal wire is actually it is a high resistance wire that is actually when it is heated it actually it turns very red, and when it turns red it can produces heat in a furnace. A top head furnace is just a furnace which is closed, so it produces heat in a furnace that is usually used for curing clay products. If you by any chance happen to be in a lab, you might find that does some assaying of different metals such as your gold, platinum. So they use what are called crucibles. So these crucibles are made of clays, and they are cured for them to be very strong. They are cured in a furnace. So some of these furnaces that are actually used for this, they are lined with what is called a camphor wire. Okay, right. Um, Now let's look at conduction in other metal materials that are not your conductors. Okay, so when you look at your ceramics and polymers, your electric conductivity is actually a very low. At times, these materials actually used even as insulators. Okay. However, when you use dopants or using what doping system, you can convert actually these ceramics into conductive oxides. Okay. So the conduction of these materials can occur as a result of movement of ions or electrons or holes. So these are your charge carriers in your polymers. Okay. Right. So both your cations and your anions in when you're talking of sorry in conduction in ionic materials, both cations and anions in ionic materials possess an electric charge, and because of they possess an electric charge and they are capable of movement or migration or even diffusion in the presence of an electric field, conduction is bound to occur. Okay, so thus, an electric current will actually result from the net movement of these charged ions. Okay, so this is the your total conductivity of an ionic material, which is the sum of the electronic and ionic contributions. Okay, so the predominant contribution, um, depending on the type of the material, can be uh, can be influenced by the type of material, the purity, and also the temperature. Okay, now now um, because the energy gap is actually too large for electrons to enter the conduction band when you're talking of your ionic materials. Um, conduction is actually done by the movement of the entire ions. Okay, so therefore, this is one of the reasons why ionic materials also behave as your insulators. So in ionic materials, the mobility of the charge carriers is given by the equation here. That's your mobility. Of course, we defined all these. You've got your charge versus the electronic charge versus the diffusion coefficients all over your Kb, the Boltzmann constant, and also the absolute temperature. That's the formula for giving you the mobility of the charge carriers. Okay. Now, mobility is how the mobility is, however, many orders of magnitude lower than the mobility of the electrons. Okay, so the mobility of the ions is actually many orders higher. Sorry, many orders lower than the mobility of your electrons. Hence, conductivity is actually very small and given by this equation where N now represents the is the concentration of the ions contributing to conduction. Okay, so impurities and vacancies increase conductivity. Okay, vacancies necessary for diffusion and substitutional types of crystal structure impurities can diffuse and also assist in carrying a current. Okay, then high temperature increase conductivity because of the rate of diffusion. Okay, I hope you won't confuse this with what is also happening in the metals. Okay, now what are the applications of these ionically conductive oxides? These are some of the applications of your conductive oxides, such as your ITO, which is your indium tin oxide. It's actually on your gadgets, your cell phones, your computer screens, your ATM machines. There's a transparent conductive coating responsible for your touch screen. Okay, so that when you touch, there is a you input, and then your gadget responds to whatever you have touched. So the main ingredient, which is actually responsible for this behavior in your electric components, is actually indium tin oxide, which is an ionic conducting oxide. Okay. Um, uh, some of the other applications include here your lithium cobalt battery function. Okay, those are some of the applications you can go. Okay, then this is a quiz also for you to attempt. Then let's lastly look at the conduction in polymers. Polymers have an energy band which has a very large energy gap. Okay, this gives them the low conductivity. Okay, what's the reason? Because in polymers, the valence electrons are actually involved in covalent bonding. Okay, so they are not free for conduction purposes. Okay, hence they are used in an hence the use of polymers actually in an insulation to prevent short circuits, arcing, and also as a safety component. Okay, however, when you introduce electrically conductive additives, you can actually lead to increase in conductivity even though they are polymers. Okay, a very good example is actually what happens when an aeroplane is struck by lightning, right? Um, you might wonder, there's a lot of movement of aeroplanes in the sky, and you a lot of storms that the aeroplane actually passes through, right? Um, in the US, it has been said that fleet an aeroplane actually hit by lightning actually more than once a year. Of course, aeroplanes are not allowed to move into dangerous weather, but at times it is inevitable. The weather simply starts from nowhere, and then you have got your lightning which is coming out. Okay, so what happens here? It's a very interesting phenomena when where your airplane is coated with a line of advanced composite materials, which are actually polymer based matrix components. Okay, so they've got improved conductivity, yeah, and they actually result in your lightning safe aircraft skins. Please research about this. You might actually find it very interesting. Okay. Hence, even when its lightning strikes the aeroplane, it moves in this conduction path, which is your polymer matrix-based composite, and it actually the current actually leaves out the aeroplane, and then the aeroplane remains in good condition. It is not affected. Okay, right. So we have got a figure here showing resistivity versus your weight percent of fibers, which is your carbon fiber, which is a conducting material. Okay. Right. Uh, Generally, this is nylon. So it is the nylon, which is maybe a non-conducting material. But when you now begin to include some carbon fibers and increase the percentage of the carbon fiber, there's a drastic decrease in the resistivity. Okay. So actually orders of to the power 13 actually. So at these low resistivities, there can be some useful conduction that can now occur in your polymers. Okay, okay. So we say doping results in electrons being able to jump freely from one atom to another. Okay, resulting in increasing in conductivity. Okay, then some um, some polymers can actually be cross-linked by special curing processes, and this also raises the conductivity. That's interesting. Okay, right. So you have what are called your OLEDs, your organic light emitting diodes. They're actually fabricated using these semiconducting polymers. So you can hear this is one of the newest model. You're folding a foldable tablet or a phone. This one you can actually fold it like this and this and all this. This is actually your OLEDs, which are polymer based, which are responsible for conduction. Okay, and the electrical processes that you can do on these gadgets. Okay, right. So here's your practical. Okay, here's your practical. Number two. Innovative engineering does not refer only to the introduction of new technologies. Okay, it also refers to the modification or the use of existing technology to carry out new functions, totally new functions, or maybe carrying out the same functions more efficiently. Okay, so um, for example, recently I met a simple music card. You know those gift cards that when you open can play some music. I recently met this card in my house, um, and I thought that it would be very good if you can change. You can use it as simple as it is. It can be actually be converted into an alarm system. Okay, you can make it in such a way that when a door opens, um, the music will sound as an alarm, maybe somewhere in another room, or maybe when you're sleeping, you put such a system maybe in your kitchen door, and then you put in a small wire that can actually transmit some energy and then play some music whenever a door is opened, or whenever a gate is opened outside, or something like that. Okay, so that can be innovative engineering. Why? Because we are simply using a simple technology, and because it is now in an alarm system, it's now performing a very more sophisticated function, but still using the same basic components. Okay, so for this practical in your groups, I want you to identify a simple electronic gadget. Okay, then using innovative engineering, modify it and convert its use into a more useful function. Okay, then I want you to prepare a PowerPoint presentation showing all the stages and information that you are going to use from the start until you have your final product. Okay, so this practical, I will give you 2 weeks to do this practical. Okay, thank you.